Cool. So I have the mic on. Can you hear in the back? Maybe, okay, it sounds pretty good. And is this, so can we use the projector? Can you see is the size decent? So I have a tendency to write both small and badly. So feel free to remind me about that. Okay, so I think originally I was supposed to talk about deep learning theory, and that's always what people expect me to talk about. But basically, let me just tell you a story. So since about the ImageNet paper is when, as everybody knows, the community completely changed. So one thing that happened, of course, is this was the old ML community, and then deep learning happened, and basically the size of NeurIPS and all the conferences multiplied by 10, and that doesn't mean that every person at NeurIPS divided themselves into 10 copies. It meant that 90% of the people were a completely new community. The community totally changed, right? It's like Bitcoin. If somebody gets 50% of the ledger, right? So the community totally changed, and then LMs happened, and it was like this. Okay, it just happened again. The community completely changed. And the theory has been the same. So back when it was deep learning, okay, that's not legible. So back when it was deep learning, and there were us theorists, we were sort of slowly making progress as deep learning just kept changing everything. And we sort of told ourselves that eventually maybe something would work out. But then LLMs happened, and it was like, oh no. And then O1 happened, and then we got another dimension. So when reflecting on what to talk about today, I was heavily influenced by this story. So I'll tell you about deep learning and large language models. And the basic plan is that I'll spend, so for those of you that are aware of the lecture notes I wrote on this, about 90 minutes will coincide with those lecture notes, I think. Maybe more like 120. But basically, the plan will be like this. So first, I'll talk about the setting. So I'll define things like an LM. Even if many of you know them better than I do, I'll still define that and talk about a little bit of the story and why things are complicated. Then, for deep networks, since I know more there, I'll do approximation theory for them. Then I'll do optimization and generalization. And then the plan right now is that the fourth lecture is actually only LLM. And it'll specifically be the computational perspective. Okay, so one of the big shifts is that the community for deep learning kept talking about them like real valued functions. For those of you that like math, you'd use standard sort of mathematical terminology on real valued functions, function spaces like that. Once we moved to LMs, it became more of an algorithmic question. And the community's actually shifted towards using discrete reasoning and computational thinking, which is an extremely interesting shift and another reason why I can't actually talk about one and pretend I'm still talking about the other. Okay, so is everybody with me? And sorry if you feel like you did not get what you paid for and you just wanted me to talk about like two-layer networks or something. So are there any questions about this plan? And yeah, there was a mention of open problems. Nothing is closed. So everything I say is an open problem. Okay, any questions before I continue? So I mean, I will do some math, by the way. In the interest of doing breadth, I'll probably, there's only one proof I'm planning to do in excruciating detail. Every other one I'll do kind of informally, but the benefit there is that for most of these, you can look them up somewhere, and I'll give sort of an intuitive version. Okay, so I'll go ahead and talk through the setting now. Okay, there's already a bar here. Okay, so I'll talk through the setting, and kind of I want to say how things changed over time as follows. So here's sort of classical ML. And I should say that I haven't really thought this out, so this is not going to be a totally clean split. But I sort of want to show this dichotomy. And just to be explicit, when I say large language model, I basically always mean, a GPT-based transformer with and without chain of thought. If that doesn't mean anything to you, you'll know within, I don't know, 40 minutes or something, 30 minutes. Okay, so the story back here was typically if you wanted to solve a prediction problem, used often a lot of geometric intuition and I'll say a bespoke model. So what I mean by this is that you would stare at your prediction problem, you would really try to understand it, and you would come up with a prediction model that really fit for it. I mean, the most painful version of this was back when kernel SVM was popular, and you were supposed to learn about RKHSs and learn about Mercer's theorem and things like that to be able to do protein sequencing or something, which is, as everybody understands, like the most ridiculous thing you've ever said in your whole life. I mean, you don't go take a biologist and ask them to go learn like a course in functional analysis. They're simply not going to do it, right? There's a good reason why that stuff died. So, so here, there started to be, oh, and I should also say that here are the training costs. I don't really know, but as far as I understand, they were basically always less than $1,000. I mean, we can check. So I'm just checking the size. Okay, I'm clearly writing a little bit too small, so I'll be careful about that. Okay, so let me go fill in the deep learning column a little bit. So one thing that starts happening is that methods begin to converge. So you don't just have a model for every single type of data and every single type of output. You start having a unification of models, mostly typically by modality. So in the deep learning era, there was sort of a best speech model, and they would keep competing. And there was a best vision model, and there was a best text model, okay? So it was a slow unification of models, and there wasn't really any geometric intuition. It was just, you get as much data as you can, and you plug it into Atom, and you use the cross entropy loss, and that's it. Okay, so there's, I'd say little intuition, lots of data, and yeah, there's only one algorithm. Okay, and now the training costs, my understanding is they started to go, they're in the thousands, plural. Okay, so then something really weird happened with LLMs, which is there's only one predictor now. Okay, for people like me that have gray hair, this is really strange. Okay, I teach a machine learning class. The whole room does not pay attention to me until I get to LMs, and then they stop paying attention again. No, it's completely ridiculous. And for that, they're like hyper focused, and they like ace everything. But yeah. So there's one model. Okay, so it's a GPT transformer. If you don't know what that means, I'll explain. Plus chain of thought. Okay, and basically lots of data. And then the costs, as everybody knows, the cost is unbounded. I saw an argument the other day where people were trying to figure out how it relates to GDPs of countries to train a model. And the calculation was that if you actually take the time it takes to train one of these models, for the GDP per that interval, it's actually above the median GDP in the world. Okay? Okay, so the cost is I'll just say unbounded. Okay? Too small? Is that what you're saying?
I have a question.
Oh, okay, good.
So it looks like LM is like a transformer-based model, right? So what is like a fundamental difference between transformer-based model with like the classical deep learning models?
Oh, yes. The question, and I'll always repeat the questions for the Zoom, right? So is that correct? Like the room mic does not pick up the question. Yeah, I'll repeat. So I'll repeat the question for the Zoom, which is that what is there a different, because it's not clear that this is just a language model with the same thing in between. I will always talk about transformers for the right column and non-transformers. And I'll discuss this in detail later, but the really big switch that happened between these is that this handles sequence data. Sequence data is scary because sequence data is how humans operate. So now this can do everything. That's really the fundamental shift. This is sequential data, and everything can be encoded as a sequence. Once you realize that, then you get really scared. These are trained on literally everything everybody knows. So of course they're smart. Good question. Okay, so I'll write out a few more things. And yeah, by the way, a lot of you are hardcore mathematicians. You're mad that I haven't written like something about a Banach space yet or something. But it's these sorts of concerns that make it hard for me to want to show you about Banach spaces right away. Okay. Okay, a few other things I want to share is that, okay, so another thing is that we have, so I'll just continue this. So here we sort of have people at least had models of data. So clean-ish data models, e.g. IID test train. Now, I should say that one interesting thing about this is this was never true. Everybody knew it was never true. Everybody still taught their classes with it, and somehow things were fine. This is very, very interesting. The example that's in many textbooks is spam filtering, which, as everybody knows, is the #1 example that does not satisfy the condition. If I'm a spammer and I know my opponent's IID, I'm going to laugh at them all day as I change my distribution on day 2, right? So it was never IID. But the point is that the algorithms still work, though the assumptions fail. Though non-IID. Okay. So you can interpret this column in a couple ways. You can view it. You can interpret it as saying that it was sort of the limit what we can achieve with a certain set of assumptions. You can say we were deluding ourselves. I mean, I remember in 2013 when the ImageNet paper came, and I spoke to NLP researchers. I spoke to top NLP researchers. Just a coincidence, a bunch of us went to dinner, and they were telling me they're still using linear methods. And they told me they use linear methods because bag of words is great. Of course, bag of words cannot do sequential data by definition. So you could actually view this as being that we restricted ourselves into a sort of mindset that prevented us from making progress. But be as it may, these things, they had this characterization that they sort of had strong assumptions that seemed to kind of inspire people to do algorithms that worked. Okay, so again, spam filtering is the least IID thing ever by definition, but you could use an IID viewpoint to construct an algorithm which actually worked okay-ish for spam filtering, okay? Okay, so this is one of the things about classical ML. In deep learning, I'll say that we were more out of distribution. So here, things like data augmentation started mattering a lot. Okay, and I'm also writing down adversarial examples. Okay, so for instance, for those of you that are not familiar, because machine learning has completely changed in the last 5 years, so there's no reason you need to know what I'm about to tell you. But one of my first shocks when the AlexNet paper came out in 2012 or 2013, when I trained the thing myself, was you could not get good test error without data augmentation. Okay, so that's just not doing what this is saying. And data augmentation is weird. You're not just pretending you understand the data distribution and making fake examples according to it. I remember I read one paper from astrophysics where they went through and they used all their brain power to construct careful data augmentation, and they compared it with just Gaussian augmentation, and the Gaussian beat their expertise. So yeah, and by the way, no one still really has a good theory of data augmentation, what it's doing. Open. So we had this shift, and then now we come to LLMs, and look, I mean, like when I talk to people that use ChatGPT, basically if it's ever not as smart as them, they're frustrated, you know? So I don't even know what to write as, like I don't even know how to define what task it's even trying to solve anymore. Okay, So I'll just say, just to be able to put something on the board. Basically, I call this a sort of universal predictor where its job is to take in, you map from a prompt and then which specifies an arbitrary prediction problem. And then people want it to map to the answer. And the crazy thing is how fast this definition has shifted. So when GPT-3 came out, people talked about few-shot learning. You had to give it a few examples. And the theorists wrote 100,000 papers in 1 month about how it can, if you feed it a training set of linear regression, it can learn ridge regression and Newton methods and stuff. Guess what? You don't feed it examples anymore. You just ask it a question and it answers it. So does everybody understand this is why I feel a little bit clownish saying that this is a deep learning theory lecture and not paying attention because everything's changed, yeah?
So I have a question. So like the data augmentation thing, like is it like a synthetic data generation?
Yeah, let me answer this question, and I'll answer it in 2 ways. So the question is, what is data augmentation and isn't synthetic data augment? So for instance, what happened when the AlexNet paper came out, the only way to get a good tester, and I don't mean a 1% difference, I mean like a 10 to 20% difference. So the only way to get a good tester on AlexNet was you did a lot of manipulations of the images and created fake extra examples. So one thing you would do is you would do random crops, things like this. There are lots of ways you could think about it. You could think about it as making the predictor invariant to certain geometric operations, but basically it seemed to create a fake training set which was much larger and it had a significant impact. For LMs, we don't do that. So that's why it's interesting. We don't do that. People are more obsessed with high quality data and actually cutting down what they have. Yeah. Yeah, so maybe I should make the point clear because I think part of the question might have been these columns are sort of not of the same type, because here I tried to sort of imply the difference between the training and the test distribution. Here you just give up on the relationship between the training and test. It's just like arbitrary in and output. So I was just trying to make it look fuzzier and fuzzier as you go right. There's another question?
So I'm probably jumping.
That's fine.
But so for LM, sometimes like there's like this test time scaling approach where like you use more tokens to improve performance.
Yeah.
So can we like explain why it's happening? Like, is it like kind of like special data augmentation for LM?
Yeah, sure. So the question is, sorry, by the way, I'm laughing a lot because I was going to talk about this. So do not worry. He asked basically the most important question to answer, which is, so there's this, so I'll repeat the question. The question is basically, what is the role of chain of thought? So for those of you who aren't aware, actually, let me try to see, because I was going to talk about this soon. Let me just try to see where I was going to talk about this so that, okay, actually, it looks like it was at least a page away. So I'll just answer the question now. So let me just tell you guys, and I'll just write it here so that it kind of continues that column. So the anatomy of an LLM problem is you have a prompt, which is a sequence of tokens. And by the way, I realize this is going to generate a lot of questions, so let's just keep it to this one, because I will discuss this in more detail later. So you have a prompt, which is a sequence of tokens of arbitrary length, okay? And the old version was, and then you make your answer, which is also of arbitrary length. Now, the problem with this is that, you know, there's no time. So if the prompt has a bounded length, and we know that transformers are quadratic time, I have to spend quadratic compute to get here. So whatever my first bit's output is restricted by quadratic time algorithms. Okay, right? Okay, now what if I can just do whatever I want and just generate fake tokens in this little gap here? That means I can spend unbounded compute before I get here. So one perspective on a transformer is that it's a differentiable Turing machine. And now you should all be really scared. Okay, so yeah. One perspective is that it's a differentiable Turing machine. I should say that this is not really true. So we cannot teach algorithms to LLMs yet. But you know. Okay, so let me just make sure that there was nothing else I wanted to say before moving on to some definitions. Yeah, there was one little thing I want to share, and then I will move on to actually defining deep networks and defining attention and things like that, and defining transformers. So is there a question about anything I put on the board? And if I seem upset, I mean, I am. Like, I literally do not know what to teach anymore. Like, every time I teach a class, I'm like, what am I supposed to talk about? So I just, yeah, I'm totally serious. I just don't know what to do. So yeah, okay. I just wanted to show you one other thing, which was I wanted to give you a refinement of this. So when I used to teach, or the way I used to often start my classes was I would point out that this was kind of the way, so here's a remark. Wait, let me try to be a little bit more organized. Let me just continue over here. My bad. Okay, so remark, I'll say the standard classical approach. Like, how do you solve a prediction problem? You do it based on one sort of decomposition. So if this is my loss or empirical risk, I've adopted the modern terminology where L is not just like this single example loss, but the average loss over the distribution or the training set. Okay, so this is my loss. For instance, I can consider this to be, here are two examples. If I do ln of some predictor, this can be the average over a training set. Okay, or if I write this, I can mean an expectation. Okay. So there's a standard decomposition which goes like this. If I want to compute the loss of what my algorithm outputs minus some really good predictor from nature, okay? This is sort of what I want. Nature has some really, really interesting process it's running, and I want my predictor to do as well as this. Back 10 years ago, I would extremely confidently write the following system of equalities and say, this is how we do machine learning. None of what I write is going to be true, but just bear with me for a second. So I can just add and subtract a bunch of times. Okay. Wait, how many people know what I'm about to write? I'm just going to add and subtract like training errors and things like that. Does everybody know what I'm about to write? That's good. That means you're all too modern. Okay. Okay. So I can just add and subtract. This is over the distribution. Then this is over the sample. Okay, so I add and subtract. And by the way, I mean, there's only one way to write what I'm about to write. There's only one way to control all these terms. Because this is something I can't control, but this is something I can control. I just run atom and I minimize this. Okay. Then I can look at nature. And I know I can beat nature because I can just burn enough nuclear power plants to make sure that I'm getting as small of ln as possible. So I can make this term as small as I want. Okay? And then I add that back in. Oh, sorry, this is actually not what I meant. I wanted to write best here, like that. What I mean by best is the best in my predictor class. Let's say I'm using two-layered networks. Then this is the two-layer network I picked, and this is the best possible two-layer network on the distribution. Okay, so I know I can beat that. Then I add and subtract its test error. And then finally, I get back to nature. Okay. So you can sanity check that I've done nothing. I just added 0 3 times. Okay. But let's just label what these things are. So this is the difference on one predictor of its error and the error on the training set. So this is what people call either concentration, inequalities, or generalization. Okay. Okay, so this one is concentration or generalization. This ln L f best, same thing. Okay, so this is concentration / generalization also. This middle one is optimization, because I'm just asking to run an algorithm that does well on the data I did see. And this last one is approximation. So you picked some class. You have some class of predictors, capital F, and both you and the best are in that. Okay, so that's why you can make this small, because you're just minimizing over that class. And the approximation, nature used whatever weird thing it did, and you fit it with the Euler network. So this is what I would say 10 years ago, or whatever, 9, 6, 8 years ago when I started being faculty. So did everybody follow? So that you could kind of break down a machine learning problem in this way and sort of attack each piece. And for many decades, you could take every mathematical paper about machine learning and throw it into one of these buckets, with very few exceptions. So when I talk about deep networks in these lectures, I will sort of bucket these things into these 3 pieces. But this is not a really good split anymore. First of all, because no one has any sense of what the distribution shift is anymore and how to even reason about it. So yeah, to summarize, what I'm saying is that back in the day, to solve a machine learning problem, you would write down this, implicitly every paper you saw had this equality, and it would use this to motivate solving some piece. Making atom better is good because it makes this term small. That was sort of the cookie cutter view of machine learning 15 years ago. Yeah?
L of F found minus L of F found equals 0.
Which one is mean 0? You mean this one or this one?
I guess both.
Yeah, mean 0, but we typically want to control things in high probability. So yeah, I should say it a little bit more detail. So this one typically will be mean 0. This one kind of subtly is, well, I don't know if everybody knows this Feynman quote that nobody actually understands math, right? They just memorize it. So I'll say this is subtly not mean 0 because f-alg was based on the training set n. So there's an independence issue here. So that's why in order to control this thing, we have to, for instance, use this ridiculous piece of garbage called a uniform concentration bound. So you have to actually control this thing, and that's the random variable you study and apply. So you have to add and subtract to make this thing mean 0. And so this is like a big tangent, but basically it's not good to think about this as mean 0. So answer 1 is no, not mean 0. So I was going too fast at first. And second, we typically control these things in high probability, which also makes it hard. Okay. But yeah, another thing I'll say is, so for classical machine learning problem, you could just work on all 3 pieces. No one works on all 3 pieces. If you want to make an LM better, you don't even think about this at all. You just try to make your test set bigger, and you try to make your training set bigger, and you try to make your training error smaller, basically. It's like all you do. And you don't change Atom. You don't change this algorithm at all. Atom has been unchanged for like 6 years. Okay. Yeah?
6 years? I thought they were more like 12 years.
I actually don't remember when it came out. Yeah, and everybody knows it was created. Yeah, actually, I shouldn't tell the story of how Atom was created in public because this is going on YouTube. But yeah, it was not created by yeah, it's a long story. Okay, so this is why I really don't know how to teach deep learning theory lectures anymore, because originally I would tell lectures and lectures about different optimization methods. But now you find out that the only optimization method used, which is literally costing tens of billions of dollars a year, and if anyone could make it 1% better, they would, It's just one method for whatever you said, 10 years. So yeah. Okay, so everybody follows. It's hard to teach. Okay, good. One more question, then I'll move on.
During training, well, where does that falls into quality system?
Yeah, so the question is, can we model distribution shift in this framework? Honestly, there are a bunch of ways to do it. If you look at the classical material on distribution shift, it would say something like you train on one distribution, and then you basically pay some sort of distribution divergence, like a Wasserstein distance or something between your distribution and the correct one. There's a paper by Scheibe and David and a bunch of colleagues from, I think, 20 years ago, or maybe even more, where they laid out this approach, and that sort of informed a lot of the community of out of distribution stuff. The problem, though, is that now OD is the framework. So that's another reason why I sort of shy away from paying attention to this. Okay, so I will now move to defining. I will now move to defining a few of these models for you guys. Okay. And I should comment that it's very easy for me to get emotional, so I'll try to chill. Feel free to raise your hand and tell me to chill and write larger. Okay. All right. Okay, so now I will tell you so the basic models we'll discuss in these days. So the first one I'll tell you about is a two-layer network. Okay, this one's really clean. I take in my X, it's an element of some vector space, and I map it into, actually, yeah, I'll write it this way. I'll say that for the two-layer case, I'll often drop the BJ because I can just put a 1 at the end of the X. For the multi-layer case, it actually does matter and does help to have the bias terms. But yeah, so I'll call this a bias. All three of these things are the parameters. And one thing I will discuss in a technical manner is that it completely changes the function class if you train both layers or not. You get a completely different solution with completely different characteristics if you train only one layer versus two layers. It is not related. Okay, it's not just like slightly better tester. It does a completely different thing. It's the best thing of it is just like a different object entirely. So I'll explain that. Okay, but this is the simplest, and this one has the most theory. So you can find an infinite number of, you can find probably, I don't know, 100 times as many mathematically oriented papers on this versus, let's say, a multi-layer network, non-transform multi-layer network.
Can you just say what are the letters at that point?
Ah, yes, sorry, I'll make this more clear. I meant to do that and I spaced out. So this is called the activation. An example is something called the ReLU. Okay, and let me define it down here. So the ReLU, if I take in a Z and I output the max of Z and 0. And then, yeah, these are parameters. So this is a scalar in R. This is an R to the D. This is an R. Okay.
More literal sense. That's the index that you're using is I, the letter is A, like it. Just say what those
Oh, yeah, sure. This is oh, yeah, sure. Yeah, this is, so there's like something attacking me. This is a J. So the question was, can I just explain all the terms in this? Yeah, so let me do it from the inside out. So you get your X, which is your input. You hit it with a vector. So you form this affine combination. So this is a regular linear predictor. But then you insert a nonlinearity, which is this, for instance, this ReLU. You scale it by a scalar, and you do this m times, and you add them together. Is it a handwriting question? Oh, it's a handwriting question. Good.
Yeah.
A V, yeah. Okay. You don't have to be polite. You can just be like, your handwriting is. No, you should just say your handwriting is bad. Like, I'm okay with this. I'd rather you just tell me my hand. No, it's fine. Yeah. Anyway, so this is a two-layer network. We have the most theory for this and a lot of theory. A lot of things here are still open. Yeah, okay. Let me also make a comment that another reason why deep learning is difficult is because the ReLU has a lot of coincidences that are painful. For instance, it's not differentiable at 0. Also, the predictor you get from this is piecewise affine. So the predictor itself has like nice piecewise affine pieces. So people generated an infinite number of papers, counting me included, doing things like talking about how you can actually formally write down a gradient flow on a non-differentiable object, counting number of regions and stuff like that. And then the empirical community stopped using the ReLU. So yeah, another reason why it's hard to work in this field. But yeah, the ReLU is a standard thing you see in theory papers. Okay, that's our simplest model. The next model is a multi-layer network. Okay, so here the way it works is I again take in my element of r to the d, and I should say that because of just my own notational handicaps, I'm typically going to write things as vectors, but as many of you know, in machine learning, we often use higher order objects. So yeah, I just won't comment on that. I'm just going to pretend you're flattening everything. So now we do something similar to before, but instead of just hitting x with a single v, I'll hit it with some matrix. I'll call it A1, and then I iterate this procedure. So I apply a nonlinearity, and then I hit it with another matrix, and I just keep doing this. Okay. I keep doing this, and then I close the brackets. So I get an AL, a sigma L. Okay, that's the object. So I form an affine combination, apply this nonlinearity, which might go coordinate-wise, or it might use multiple coordinates at once. Just keep forming these affine combinations. I do this in stages. Okay, yeah. So I put a subscript on them so they can be different, yeah. In practice, people usually only use like a small number of different ones, like 3, and just repeat them in a different way, interesting ways, but. Okay. Okay, let me make some other remarks about this. So so one remark is that this is naturally has a multivariate output. For basically everyone in here that isn't a professor, back in the day, we had to learn about a lot of binary classification methods and ways to combine binary classifiers into a multi-class output, and how difficult it is and all the things that can go wrong. It's very nice that this is just naturally a multivariate predictor. So the output can also be, yeah, some large dimensional output. Okay, so naturally multivariate, but fixed dimension. So this, as I mentioned, was the big thing that changed with transformers, that they became sequential. They can have a variable length input and output, yeah? Oh, no, what I just meant was that in the univariate case, I can always, sorry, in the single layer case, I can just put a 1 down here and it's equivalent. But in the multivariate case, I can't manipulate, here I can manipulate the input, but over here I can't just like insert ones in the appropriate place. And I should say that in practice, it's very spooky to me. I typically run my experiments with them off, but then I'm like always paranoid. So yeah, it was just a very technical comment that for this, I can insert the 1. For this, I can't insert ones everywhere. That's all. It's not a deep comment. Okay, another thing. Oh yes, so today there are many variations. I won't talk in detail. I won't discuss convolution and RNN in detail. I will just sort of point them out, but these are models that allow that processing of sequential inputs that are sort of between a fixed dimensional deep network and a transformer. I just will only sort of refer to them, I'm limiting the scope. I will only mention them tangentially. But I can take questions about them if you're like, oh, why is the RNN weaker or something? I might prove that actually at one point. So we'll see. Okay. Okay, and so there isn't that much theory about these things. It's still pretty wide open to really say why these are better than these. So in practice, the depth kept increasing and the architecture kept changing. There's almost no theory about why that happened. Okay, so any question about this before I define a transformer? And yeah, I'm not doing any math yet. I'm just telling you definitions. We are 1.5 pages from a proof if anybody's freaking out. Actually, I'll just make sure I cover a proof in the last 20 minutes at a minimum. Okay, I'll just give you that promise. So that it's not just like all words. Sorry, what'd you say? Yeah, somebody needs to scratch the itch. Well, I mean, I was brought here to like pretend I know math, right? So anyway, so are there any questions about this? Okay. So I will define a transformer, and I'm going to do it as a, I'm going to write down sort of a semi-modern transformer. So what I'll write is somewhat related to what the Llama 3 architectures look like. This field moved fast, and what I'm saying is not exactly what's used in the companies, but yeah. Okay, so yes, okay. So now let me tell you about, I'll call it the GPT architecture. This is AKA a, sorry, I'm gonna need more space. I'm gonna call this a causally masked decoder only transformer. So for reasons of the usual, when people say transformer, they cite this attention is all you need paper. However, of course, the lineage of the transformer goes not only back decades, but there were certain critical decisions made after the attention is all you need paper, such as the decision to be autoregressive, which are absolutely fundamental to the success of LLMs. So that's why I'm focusing on this architecture. There were many interesting and intelligent decisions that were made along the way. Okay, so the modern architecture looks sort of as follows. So, sorry, I'm just deciding how I'm going to use the board. Okay, so I'll show you this way. So I take in a sequence, and I'm going to tell you what I'm going to do on some late sequence element xt. Okay, I'm going to tell you how I process xt given the remaining part of the sequence. So what I'm going to do, the first thing I'll tell you is that I'm going to produce what's called the sequence to sequence mapping. So I'll call these all x0 as the input. And so the first thing to know about a transformer is that it forms an iterative sequence to sequence mapping. So I'm going to map this sequence to another sequence. I'm going to map this sequence to another sequence. And the effective depth is how many of these internal sequences I get. That's absolutely correct. Yes. So this will be like sorry, how many yes, how many are in Rush. So your last name is probably gets a single token, and it'll probably just be xt by itself. It's probably common enough to with the capitalization. So and this one it can one-shot, so it should get the correct answer without chain of thought. But okay, anyway, so yeah, and I should have repeated the question. The question was what is this actual sequence we are dealing with? Okay, and so the way a transformer works internally is I find it, you can read many expositions of transformers. This is just my opinion. I find it easiest to think about it as an iterated sequence-to-sequence mapping. So I'm going to tell you how I mapped this to another sequence. Yeah, I'll repeat the question and explain just a second. Yes, so the question was, what are these objects? So I'm going to treat the objects as elements of a fixed dimension vector space. So we're just going to consider these to be in R to the D. I should say that that is not exactly what transformers do. What transformers do is they read in tokens, so discrete objects. And one of the first parts of a transformer is to embed those in a D-dimensional vector space. And it varies whether that step is learned or not. So it's not really fair for me to call this the D-dimensional vector space, but it's easiest for us to consider it a D-dimensional vector space. So these are all elements of R to the D. And these are in some other dimensional vector space. Let me just write one more thing down. So I'm going to map, and I'm going to tell you how this works, but I'm going to map this way, and I'm going to do it again, okay? And I'll keep doing it until I get some final final layer L output. Let me just explain this, and then I'll take the question. So I'll do this for the whole sequence, and I'll do it for this. And when I start making my output, what I'll do is I'll take this, I'll apply a softmax. So I will sample a new thing. I'll say sample proportionally to just the exponential, the softmax, whatever you want to call it. Actually, this isn't formally correct, so let me just add a little nuance. There's an extra matrix here called the unembedding matrix. So I'll just write that in. And if you're not an expert, don't worry about it. So I'll form this softmax. There's just another linear operator that I apply. And I'll sample from this. This will be what I'll call Y1. And then Y1 is my first output. So I do this layer-wise thing, many layers. This is an L up here. So I do, so I say the first approximation of what I'm doing is that I'm doing sequence-to-sequence mapping L times. And I do something sophisticated to go from one to the other that I'll tell you in a second. What was the question?
Well, I now have two of them. The first is when you do the sequence-to-sequence mapping in a modern architecture, is this a residual mapping or not?
I'll explain that, yeah, in detail.
And the second question is, when you have the final sequence, how do you map from that to the softmax?
Yeah, so I mentioned this nuance, which is that this I'm treating as an element of R to the D, but things come in tokens. The tokens are one-hot encodings in a higher dimensional vector space. And here, similarly, I need to map back into a dimensional vector space where the dimension is equal to the vocabulary, and then I apply softmax to that to sample.
And you just do that to the final element in the sequence.
Yeah.
Yeah.
Yeah. And now all of you can at least see that I didn't tell you how I go from here to here, but assuming the computation from here to here is bounded, then the computation from here to here is bounded, but then this chain of thought thing we mentioned gives us a way to spend unbounded computation between these two. And that's why it's more powerful. This is the earlier question. Okay, so the next thing I'm going to tell you is now I'm going to tell you what goes on inside. And I did promise you like some math before we finish. Oh, and if anybody is like totally mad that I'm spending so much time on definitions, you can just tell me afterwards and I can adjust, because I did write down like a lot of math in here. I'm just not getting into it yet, but I personally don't mind. So I'll need feedback if somebody wants me to adjust. Okay, let me tell you what's going on from here to here. Okay, so this relates to this question we just got, which was, actually, let me see okay, I'll write a little bit bigger. So, okay, actually no, it'll be too confusing if I change the orientation. Okay, so here's x to the t, and I'm going to tell you xt0. I'm going to tell you how I'm going to get to, excuse me, xt1. So the form of modern networks has a very interesting decision, which is the first question that was just asked. They use something called a residual connection. So instead of applying some mapping from here to here, the intuition is that because of training or whatever, it could easily go wrong. You could get a junk output and get stuck just always outputting junk. So modern networks, they use something called a residual connection, which is by default, you're doing an identity mapping. And the complicated stuff you want to compute, you just add that into this, okay? So formally, what I'm going to tell you is that to compute xt1, it's going to be the input plus some f applied to it, okay? And you do some tricks to make sure that this thing is sort of stable and not too big, so that by default, you're doing an identity mapping. The intuition is that you're not deleting too much information by default, okay? And by the way, this was one of the critical decisions in the evolution of deep networks. So even though it looks like deep networks are moving fast, actually there's actually a very small set of key decisions that did not change every few years. And the residual connection is one of them. Once people started using it everywhere, it's not left for a decade. Okay, so I'm going to tell you how to compute this. So there are two components. The first one is the attention block. And then we add that in. Okay, so I take the input, I form the attention block, and I add that in. Something kind of like this. And then I do this again, but with what I already showed you. This is called a MLP block. MLP means multi-layer perceptron. It's just the terminology people adopted for this is sometimes kind of like a multi-layer network, the same as I just defined on the board you can't see right now. Yeah, the board you can't see right now. Okay, so what I've told you is that I'm going to split this thing up into two parts. There's going to be an MLP part, and there's going to be an attention part. Okay. Unfortunately, reality is not so simple. This is not exactly what I told you, but I'll tell you this one first. So what the MLP does is it takes in its input. The first thing it does is it normalizes it. This is one of these decisions in deep networks that as soon as everyone started using them, it did not go away. So normalization layers are from the 60s or so. It's hard to trace the original lineage, but the first widespread use was in the 1960s. And then they started being really used when Alex Krizhevsky came with his massive brain and basically rebooted deep learning in 2012 with the ImageNet paper. So ever since Alex Krizhevsky started heavily adopting normalization layers, they haven't gone away. They've changed what they are. Nowadays, we use a very simple normalization layer called an RMS norm, where you just divide by the L2 norm of the batch. But anyway, so you first do this, and then you do an MLP. People call it an MLP. This can be one of two things, and I request that we do not get too tangential here. So it's either what I just told you about, which is the multi-layer network. Or there's another option. Does somebody know what the other option is? Do they want to tell the audience? Okay, good. I'm telling you something new. In modern networks, people use something called a mixture of experts in place of the multi-layer network. You can just view this as a computational trick. So it's a way to save a constant factor, a significant constant factor in compute on the MLP. Basically, you compute like a subset of the MLP only. But constant factors on a $100 million training cost are pretty cool. So all modern networks actually use this. They don't use the standard MLP, but you can just think about it as a computational trick on top of that. I think that's not too rude to call it that. It's a good idea, but it is, yeah. Okay, so at least people kind of understand what this MLP thing is doing. By the way, when I say I kind of understand it, I definitely can't prove any theorems about it, but yeah, that's what it is. Yes.
Okay, so I guess my question is sort of like, what are we trying to do from going from the like the 0 to the L layer? I mean, could we describe that in a high level?
Yes, that is a very good question. So let me repeat the question for the Zooms. The question is sort of intuitively, what's going on through these layers? What is like the problem I'm solving with each of these sequence to sequence mappings? We certainly can kind of say what we want XTL to mean, because if the question is, here's a matrix, what is the smallest eigenvalue, okay? Then we kind of want this to just be the token or the first token of the smallest eigenvalue. So we know that this should be like something that maps that we sample this is smallest eigenvalue. But then what are all these and what are all these? So the best answer I can give you, to be totally honest, is I don't know. There is a lot of work on what the intermediate layers do, and it is an extremely active area of what people call mechanistic interpretability. What a lot of people like the most in this literature is actually the Anthropic blog. So the company Anthropic, they have a lot of research on interpretability, and they have very nice blog posts where they kind of go through the intermediate layers and say what they think they're doing. It's a very active area. And actually, a lot of people are, especially mathematically oriented people, are thinking about experiments that can say what these are doing. But let me just give an example. So one thing from the Anthropic blog, going back, what they did was they took the middle layer and they did sparse coding on the middle layer. So you do standard training. You don't modify the training process at all. You just look at what the middle sequences. And I asked the author, actually, I asked him personally, and I asked him which layer using, and he said basically the middle is the best. Take the middle layer, you do sparse coding on it, and you look at the sparse coding vectors, and it turns out it has a lot of semantic meaning. So for instance, he told me that if this is a sentence in Japanese, and this is the token corresponding to bridge, okay? This is like bridge in it's like in Japanese, or sorry, like I guess katakana, maybe hiragana in this case, but actually I shouldn't pretend I know what I'm talking about. So, but it's a tokenization of one of the Japanese scripts, and it's a sentence about San Francisco, and it says bridge here. If you look at the sparse coding, there will be a code vector they associate with Golden Gate Bridge, which they say is on. Now, you could say that interpretability is like a fuzzy science and all these things, and like, get me fired by like extracting this quote from the YouTube, but that is the best. People think that the middle layers have more semantic meaning. Yeah, but this is an ongoing, this is a very ongoing area of research, like trying to understand if the middle layers really are doing things. There's no short answer for it, but maybe I can show you some papers after or something like that. It's a good question, yeah? So I didn't explain what goes on in here. There's a lot of softmaxes in the network, if that's your question. Well, okay, let me just be really precise. To produce Y1 from XTL, I do sample using a softmax. However, I haven't filled in everything here. There are other softmaxes inside the network. Maybe that was your question?
XT minus 1L also sample as softmax.
Yes, okay, so good. So yeah, there are many moving parts here, and I haven't. Okay, let me say it this way. So, and I should also say that there's something I left out here, which is there's a temperature parameter or an inverse temperature parameter. So if you hear about a temperature parameter that you can actually feed in the OpenAI API, you can just feed it a parameter. It's this scalar right here, which makes this distribution more uniform, more concentrated. But yes, when you're doing training, the way training works is you have sequences. Yeah, actually, I'll just explain this now. I don't remember where I was planning to talk about this. So to train such a network, the first stage of training, the so-called pre-training stage, you have a bunch of sequences. You do produce all these XTs here, but you don't do the sampling. You discard. You don't do any sampling. What you do though is you do cross entropy training between the observed token and the distribution that you see. So you do cross entropy between those two. So I'll look at the distribution I get here, I'll look at the next token, and I'll form a cross entropy there. So I don't do any sampling, but I use the intermediate tokens. So I realized I got a little mixed up. So let me just say the sentence clearly. I form this final layer. I produce the distributions. I use it to compute a cross entropy loss during training, but I never do the sampling. Then when you generate, when you ask ChatGPT a question, so it discards these, it doesn't need these, but then to generate a sequence, it does a bunch of softmaxes. Okay, I think I kind of redeemed myself. I hope that was clear. Okay. Okay, and I'm like mentally adjusting that I will probably actually not get to a proof in this 90-minute session, because I think in the interest of being a little bit more coherent, I should not. Like if anyone's upset about this, just come to me at the break and then I'll just like double the number of proofs in the next section. So no, I'm actually serious. I'll just do that. So okay, so I mean, it's actually easier for me to do the proofs because I'm out of my depth when talking about the empirical stuff. So okay, now let me tell you the attention, which indeed should be done very slowly. Okay, so let me point out that I haven't mentioned anything that uses sequential input. So when I went from here to here, the MLP is fixed dimensional. So it's only taking the output of the attention as input and it's making this output. But according to it's just seeing token to token mapping. It is not seeing outside a single token. Okay, so it is definitely not seeing the context that it's in the gold, it's in San Francisco or something, and there's a Golden Gate Bridge. It doesn't know any of this. It just sees the word bridge in Japanese. Okay, so I have not explained how this thing actually reads in a sequence yet. Okay, sorry, I'm looking at my notes just because I want to make sure I didn't forget some like critical thing I meant to tell you. Okay, so let me tell you how the attention works. And again, there are many ways to teach and understand attention. If you're familiar with attention and I write something you don't expect, just ask me after and I'll connect it to your version. For the experts in the room, I'm not going to use a matrix view of attention. I'm going to use a sequential view of attention. So if you know one or the other and you don't understand what happened, just ask me afterwards. So here's what the attention is going to do. Oh, wait, oh, sorry, I'm destroying the markers. I feel bad. Okay. I didn't notice until now I had done this. Okay, that's very bad. Okay. Okay, so the attention block, similar to, so the attention block is going to do something that I'll tell you about in a minute, and then it's going to pass it through an attention layer. I'm going to tell you what the attention layer does first before telling you what this is, because this does something a little funny that's not going to make sense until I tell you what this is. Okay, so the attention layer operates as follows. So the goal is to pick, I'm going to call it PT, which is, I'm going to write delta T. So delta T, I mean the simplex over T things. So this is a convex actually, I should just write it down at least once. So delta T is going to be vectors in R to the T such that they're non-negative and they sum to 1, okay? So these are probability vectors of dimension T. Okay, I'm going to pick a PT where, and I'm going to output the sum of, I'm going to take the convex combination of essentially what I saw before. The only caveat is that I'm going to have another matrix here. There's another matrix here, but I'm going to output everything that came before me. Okay, so let me explain this carefully. So this is, I'm summing from 1 to T. So this is everything, the entire sequence. Okay, this is all the elements of the sequence. I'm passing them through a linear mapping. And what I'm doing is I'm taking a convex combination of them. So this is the output of the attention layer. This is what's going to come out of here. If you're confused, just wait for me to explain a little bit more. This is equivalent to the standard definition. Okay, so my goal is to pick a convex combination of everything I've seen before and find a very nice convex weighting that I pass on to the MLP. Okay. By the way, for those of you who haven't seen this definition, I'll explain the equivalence later. Those of you who haven't seen an attention at all, this might seem weird because, I mean, one of the points is that typically this dimension and this dimension are the same or they're related by a constant. So, you know, you don't have enough bits to pack in the entire context of size n. You can only look at a few things from the input. But the point is that at every place here, I'm going to choose a different PT. I get to pick PT at time t. Okay, so this is the first thing to know about an attention. It needs to construct this convex combination PT that kind of pays attention to different things in the context. The context is what people often call x1 through xt, and then combine them. Now the question is, how do you pick PT? So here's the formula. So the formula is PT is chosen proportionally to another softmax. And I'm going to write it this way. Okay. So I'm writing KT, sorry, this should have been an S. Okay. KT transpose KS, where QT is equal to a linear mapping of the current input, and KS is equal to a linear mapping of the previous ones. Okay? So to form PT, what I do is I produce one fixed vector, I inner product it with some linear mapping of all previous tokens, and then I sample according to the softmax. And this is a modern attention. Yeah? Oh, sure. I think his hand was first. No, you go ahead. Your hand was first. Sorry, what is the question? Oh, sorry. So this is from S equals 1 through T. So you can think about it as summing over the entire sequence. Okay, so what I'm doing is I take this matrix WV, I hit everything with WV, and then I'm applying the coordinates of P to these and then summing them together. Yeah, I'm careful with my indexing. So this is a summation from 1 to T. I see everybody, including myself. Oh, that's your question. Sure, yeah. When I'm producing token T plus 1, then this will be T. Everywhere that I have a T here will be a T plus 1. Yeah, maybe that's an important point here. So yes, T really does mean this T. It is not a constant. So when I do this one, let me say it this way. P is in 1 dimension, P is in 2 dimensions, P is in 3 dimensions. And this is why people call this a causally masked transformer, because I only have a convex combination of myself and everything before me. Okay, yeah, that's a very good point. So this here is not a constant. And this is the why people call it causally masked. And you had a question also? Yes. Let me get to that in a second. Let me just explain this causally masked thing a little bit. So for those of you that have seen a matrix version of writing this down, the matrix version, you do this causally masked form, you have to multiply in this masking matrix. And to my taste, it ends up being conceptually more complicated. So when I teach, I always use this one. When you implement attention for efficiency reasons, the matrix version is more efficient to implement. But I find this one conceptually easier to teach. So for those of you that know both versions and you're confused, this really is a way of writing it that actually was in a bunch of these linear time attention papers that I adopted from those papers. So this is not my idea also. Let me answer the question on why this is called attention, because to produce the input to the MLP, people view this as attending to different elements of the sequence. Because the dimension of this is really close to the dimension of this. So I might be fuzzing the details. I believe in llama. I believe the dimension here is 4 times this one, but it even might be equal. So you can just think of this as being the same dimension. So you don't have much information here. You can't compress the entire sequence. You can only look at a few things. And one thing people do is let me reuse this board because this is kind of important. Actually, sorry, I'm going to, okay, this is a little bit low. Okay, I'll do it. I'll do this. I'll just put this up. I won't edit that one anymore. So I can form a matrix. So I can form a matrix at time t where all the dimensions are, all right, t by t. Okay, so this matrix is an R t by t, and this is it's called the attention matrix. Let me see. Okay, yes, you can still see that board. And so what this matrix contains is these distributions as row vectors. Yes, as row vectors. So I was worried I got like columns and rows mixed up. Okay, so it contains these. Okay, so what is this matrix? It's not a doubly stochastic matrix. This matrix has a distribution per row, but I'm imposing no structure on the columns. And this matrix is sort of the first thing everybody reaches for when they try to understand what an attention is doing. And when I was first learning about transformers, I was really late to the game. One of my favorite papers to learn about them was the AlphaFold paper. That's where they do protein folding, and they show what the attention is doing. And some of the matrices just look nearly diagonal. Sorry, that was not. Okay, there we go. So some of the matrices look nearly diagonal. I'm pointing this out because it gives a strong meaning to the word attend. Because from that equation I wrote, there's no reason to believe PT is sparse. But that's another miracle of attention, which is that you just run atom on this thing. It very often picks very sparse matrices, where after applying the softmax, it's very large in one coordinate and very close to 0 in a bunch of others. But this is not uniformly true, but very often these matrices have very clean structure. And so that's why people call it attend, because in order to compute one output, you can see it really just attended to one input. So that it becomes like a discrete thing. That's why they call it attending and attention. That's the lineage. I know that was a long explanation, but I felt like I had to give this matrix to explain this. Okay. So if anybody has questions so far, I'm going to check my notes to make sure I didn't skip something important. I know I didn't define what the whole attention block is yet. I won't forget, but I'm just reading my notes. Feel free to, yeah?
So for the definition of KN, it is defined via linear operator of XS.
Yeah.
XS is the whole token for previous RD input.
Yeah. So it's, sorry, this was a mistake. This should have been a W sub K. These are different matrices, but yeah, this S, this is for all possible S. So this ranges over 1 through T.
Okay.
Yeah. Another way to look at it is that if I look at entry, if I look at entry IJ here, this is going to be it's going to be proportional to, it's going to be computed from XT, like QJ transpose KI. It's just not exactly that because this is after softmax normalization. So
The question is that we want to pick the PD from a syntax that's delta T. Is that because we want to form a transition matrix so that the row sum is equal to 1? Because we wanted to represent the transition.
Well,
or we just want the convex combination.
It would be very interesting, and yeah, I do point out that it's not a doubly stochastic matrix, but yeah, perhaps there is some sort of Markov view. I don't know of any paper that uses that perspective. it was a bunch of empirical coincidences that led to it being an exponential. So it's true that the attention is all you need paper fixes an exponential, but all the previous papers on attention actually tried many choices. So there's even an NLP paper out of Google. So the same people that made it, the attention is all you need paper from about a year or two before, where they tried many variants. So there is some many variants which in particular are not L1 normalized. So I can't tell you with like any IQ whether the L1 normalization is a coincidence or not. And yeah, anything I would say is basically pure speculation and probably wrong. So I apologize. Yeah. There is like a lot of L1 normalization in modern deep networks. It's like everywhere, but I don't know if it's a coincidence or not. This isn't the only place. Sorry. Okay, any other question before I maybe say some remarks? And then, yeah, feel free to give me feedback. I will basically force myself to be mathematical when we come back. I'll just like summarize and skip some material. But yeah, any questions? Because it's important that we understand these basics when I talk about everything else. I still need to define attention block, which I can do in the remaining time, and anything else anyone wants to ask. Yeah. Yeah, okay. So I'll just define attention block and also make a small correction. Oops. Yeah. Sorry, I'm staring at my notes, just like really scared I missed something. I mean, I know I know everything I wrote on the board all my definitions are correct. I'm just worried there was something I figured out that I wanted to share and I forgot, but okay. Okay, there was one thing I forgot, which is that when you sample this exponential, you actually square root by a dimension I'll call d embed. I should say this embed is used in many places. So actually, sorry, I'll just call it d double prime because I forgot the correct terminology and I don't want to, but d double, this is the dimension of, this is the output dimension of WQ. So WQ maps from D and from D to D prime. Sorry, from D to D double prime. Okay, so that's the inner dimension here to sort of normalize this inner product. So that it's, yeah, to sort of normalize inner product. So that's just one thing you might see that's different. Okay. So the only other thing and then yeah, we will be mathematical. I promise we will be mathematical when we come back. So the only thing I wanted to tell you was a bit of history. I know that's like very soft, but it's just something I wanted to share before we close, because I think the history is very interesting. Also, even though like 100 million transformer papers come out per day, the number of ideas that stick, like I say in the architecture, is actually very, very small. So if you look at 1943, that's the McCulloch-Pitts paper, that was the first multi-layer network. So that was, okay, I won't write it on the board, but it was sigma L, AL, blah, blah, but with a non-differentiable activation. And then actually preparing for this lecture, I didn't realize it was already in the 60s that people not only switched to doing, they switched the hard indicator with the sigmoid, and they started using gradient descent. So in the 60s is the earliest reference I have to training networks with gradient descent and doing this. That was by Amari, who's known for a million other things too. The convolution, the ReLU, and the normalization layers, those are all from the 70s. That was another Japanese researcher named Fukushima. So yeah, he has this really short paper that summarizes it. And he actually ran it in hardware too. You can find videos on YouTube of it running in hardware. So yeah, ReLU, convolution, and normalization. And then that was 79. And between then and the 2010s, there were many developments of RNNs especially. But for me, a lot of things jumped until 2012. So that's when the ImageNet paper came, and the ImageNet paper basically popularized old ideas and got it running on GPU. But it was, I put a lot of credit on Alex Khrushchevsky, who made AlexNet and got this thing running on GPU. So yeah, just getting it to run on GPU might be actually the main thing that changed the world. And then after 2012, this residual idea, it was in earlier papers, but it really came with two papers, this highway network paper and the residual paper. Both papers, they came out nearly concurrently. Well, the highway network paper was first, but so they had this idea. And then, yeah, ever since then, and then attention was 2017. Sorry, this version of attention was 2017, based on papers from the 5 years before that. There's like a long lineage of attention papers. And then 2018 was GPT, and then since GPT, things have not actually changed that much. So, and GPT was the idea that you use the causally masked attention, which makes this a natural generative model for sequences. Okay, so that's the real punchline of transformers compared to other models, is that they're sequence to sequence. We can write anything that humans can do as a sequence, as far as we know. That's something called the Church-Turing thesis. So yeah, so it makes things sequence to sequence, and it's naturally a generative model. I should write that down somewhere. So yeah, the point of this is that it's seek to seek, and it's generative. And that basically, those are the two, I'd say, essential properties. Because now you can train it on all human knowledge and have it generate all human knowledge. Okay, so I have 1 minute. Somebody want to ask a question? Yeah?
You said that this is roughly following notes. You said like the first note here.
No, there are no notes for this. Sorry. Eventually. If your question is what is the source material for this, I'll say that this architecture is roughly what's in the like the Llama papers, also the Llama GitHub. These days, the best way to figure out what an architecture is just to read the code. I'm sorry, like read the code on GitHub. So a lot of things I say, I'm very confident because I've read the code on GitHub. That's why, for instance, you can just, so I mentioned that this RMS norm, by the way, I realized I forgot to tell you guys about positional encoding. That'll have to wait another day. But yeah, anyway, so to have one resource, I'd say the Llama is good for the mixture of experts. There's this paper called Mixtural of Experts out of Mixtural where they really popularize using mixture of experts. This version of attention is, there's a group at MIT that works on linear time attention. The main person working on it is a PhD student named Songlin Yang. And it was in her papers that I first found this way of writing down the attention. I think between those things, you can find a union of what I told you. Oh, and this terminology, calling this a residual stream. So people call this a residual stream now. And that terminology is from Anthropic. So I do plan to publish notes on all of this, but right now, all these things are not in any one place. Sorry. We're technically over time. It's up to you whether I take another question or not. Okay.
I have a question. So I'm want to understand a little bit about evolution here. So previously, I think like before the attention probability papers, there's like sequence to sequence learning, and like there's also like some kind of like pre-training paper concept. So what is the fundamental difference between like sequence papers with the attention?
Okay, so I should say that sequence to sequence is a very loaded term, and it was originally used for RNNs actually. I think there's a paper which is just sequence to sequence by Ilya Sutskever, I think, and Oria Vinyals and Po-Ling Loh is my recollection. It's from like 2011 or something. I will say that I think the shortest answer I can give you is that the importance of thinking on a sequence to sequence level is by treating a sequence as a unit, for instance, you decouple the length of the input and the output. So for instance, with this generative model, if I want to generate a translation, I can do it in so many ways. Okay, for instance, I can read the thing in, and then I can generate my translation. I can start generating it in real time. I can generate it in backwards for languages that read. You know, I mean, you can do so many things. And I would say that that is why the sequence to sequence concept was important. And I mean, that's also, yeah, so I think that's the shortest answer. I'm a bit out of my depth answering this question, I have to say. That is my shortest answer, is that you treat a sequence as an object, which means it can have varying length on the input and output. It's up to Siva. I mean, I'm standing here, so you can like come ask me alone if you want.
It's,